right, so now let's take a look at inverse functions. You probably have seen inverse functions before in your conventional algebra course, and you probably have a graphical understanding of what an inverse function is. For instance, this function f of x equals 5x minus 7. Let me just draw it down here. 5x minus 7 means slope 5, y-intercept minus 7, so it looks something like that when you think of y as a function of x. But if you turn this on its side, or in fact it would actually be rotating around this 45-degree line, and you considered x as a function of y, you put y here and x here, well, instead of y-intercept being minus 7, the x-intercept would be minus 7, and instead of slope 5, you'd have slope 1/5, so it would look something like this. Okay, sorry, I didn't do it very well. Right. But the point is that you have another function that gives you the original value back again. If I took some value here, x, and I found f of x up here, and then I went over here to the same location, y, and went back up to x, then this value here would be exactly the same as this value here. All right? So inverse functions do have a graphical explanation, and an algebraic explanation also. To find the inverse of this function, you basically solve x for, you write this as y, and you solve for x, and that will give you the inverse function. Okay. All right, so let's look at some general relationships with inverse functions. This is, suppose we have two functions, so let's draw two circles here, x and big Y, and we have f goes this way and g goes the other way. So the inverse function always has to go the reverse direction of the original function. Okay, and you're saying that suppose that for all x and x, and for all y and y, y is equal to f of x if and only if f is equal to g of y. So what does that mean? So here I have x here, and here I have y, which is f of x. So this is f, and this is f of x. On the other hand, if I call this y here, then it turns out that this f, if I take g of this y, then that's going to take me back to x. Okay. So you can see that if you go, if you first take f of x and then you take g of the result, you get back to x. So that's just what this is expressing here. Okay, and then this proof really is just expressing the same thing. It's a substitution proof. But you can see from the picture that that's what inverse functions do. You follow the arrow one way, you follow the arrow back the other way, and you get back to your original point. Okay. All right, now, I should say at this point, you probably know that a function has only one inverse. But at this point, we don't know that there is only one inverse. So we're going to define an inverse. Okay, so given a function f from x to y, we're going to define an inverse. Now, there may be some functions that have no inverse, but for a function to have an inverse, there must be a function that satisfies these properties. F of g of y is equal to y. So if I have some function g here, so it's that whenever I take y here, whenever I take g of y and apply f to that, then I get back to y again. Also, the other condition is that if I have any x, whenever I take f of x and apply g to that, I get back to x again. Okay, so you can see from the picture that basically you're just going back and forth. Okay. Now here's another example. You can follow this. You can find inverses. This is, you find these the algebraic way that you found in your college algebra class. Now, as I mentioned, some functions don't have an inverse. In fact, most functions don't have an inverse. Okay, so in fact, it turns out that a function has an inverse if and only if f is a bijection. If and only if f is a bijection. Okay, and then bijection, remember that means one-to-one and onto. Okay. All right, so we're going to prove the forward direction, and we'll ask you to prove the reverse direction. What's the forward direction? So we're saying that, so let's see, how are we doing? So we're assuming that f has an inverse. First, we're going to assume that f has an inverse, and we're going to show that f is a bijection. And you have to go the other way around, that if f is a bijection, then f has an inverse. Okay, so let's see. So so we're assuming f has an inverse. Okay. All right, so let's think of the idea of how we're going to prove this. Again, we want to draw a picture. Okay, so I have put the conditions here and copied them so we can do some drawing. And okay, all right. So remember that we're trying to prove the forward direction of this proposition. Okay, and then this is the definition of inverse. Okay, so we're assuming that f has an inverse g. Okay, so we can assume g is an inverse of f. Okay, so let's first prove that f is one-to-one. Okay, so what do we want to show? Remember, the way we want to show that if x1 is unequal to x2, that means that f of x1 is unequal to f of x2. That's what we want to do. So this is to show. Okay, I'm just putting this off on the side. All right, so let's see. So we'll suppose that x1 is unequal to x2. Okay. All right, now we have that g of f of x is equal to x. So we want to consider f of x1 and f of x2. So we have g of f of x is equal to x. Okay, so then, so by the definition of inverse, g of f of x1 is unequal to g of f of x2. Okay. All right, and so I could say in substitution. Okay, because I know that x1 is equal to this and x2 is equal to that. Okay. Now, here we have two function values that are different. Can you see that it's impossible for f of x1 to be equal to f of x2? Because if f of x1 was equal to f of x2, then g of f of x1 would be equal to g of f of x2. So this contradicts f of x1 is equal to f of x2. Okay, for otherwise we'd have g of f of x1 is equal to g of f of x2. Now I can probably rearrange this writing to be a little bit nicer, but this is kind of the idea. The idea was that if f of x1 was equal to f of x2, then the g's of those two f's would be the same, but they're not. Okay, so let's do onto also. Okay. Okay, so you want to show so that for any y, there exists an x such that f of x is equal to y. Okay, so now by the definition of inverse, remember the definition of inverse had two parts. We have g of f of x equals x. We also have f of g of y is equal to y. So by the definition of inverse, f of g of y is equal to y. Okay, so what does that mean? This g of y is in x. We have found x such that f of x is equal to y. So we'll let x equal to g of y, then f of x is equal to y as required. Okay. All right, so that's kind of a rough idea, the way you kind of think this out. And let's go to the write-up so we see how it's written more formally. Okay. Okay. All right, so here's how we do one-to-one. Okay. So suppose then that f of x1 is equal to f of x2. Now it looks like in this one they proved it the other way. They're assuming that the two function values are equal, and that means that the two original values x are equal. So this is another way to do it. Okay, so they apply g to both sides, and then notice that g of f of x1 must be equal to x1 by part b. Okay, so f of x1 is equal to f of x2 gives me x1 is equal to x2. So this is a more direct proof than the one I did on the page. That's fine. Sometimes you can try it both ways. You know that you can prove one-to-one two different ways. Okay, all right, so that's the one-to-one. Now for onto, it goes pretty much the same thing. Suppose we have a y in y. Okay, then since g is a function, there's exists a unique x1 in x such that g of y1 is equal to x1. Okay, but then for this x1, we can take f of x1, which is equal to f of g of y1 is equal to y1. Okay, okay. So we do find a x such that f of x is equal to y1. Okay, so that's fine. So you'll have to go the other way. You'll have to assume that f is one-to-one and onto, and show that there is an inverse such that there is a function that satisfies this. Now you may have a little trouble getting started with exercise 90. The question is, you're assuming that f is a bijection and you want to define the g. So let me help you define the g here. All right, so we're going back here. Let me erase some of this stuff. We're still using this condition here, so I can just get rid of this for now. And this here. Okay. All right, so now we're going to start with the other one. We're going to start with f as a bijection. Okay, and we want to define g. So let's say given f is a bijection. So remember, I'm proving the other way now. I'm proving this way for the if and only if proof. Given f is a bijection. Okay. Now for any y in at y big Y, since f is onto, there exists x in x such that f of x is equal to y. Okay? Okay. You also have since f is one-to-one, it follows that x is unique. There's only one. Okay, there can't be two. There can't be two different x's that map to the same y. Okay, so I'm going to define the function g, which goes from big Y to x by g of y is equal to x, given above. Okay, so I said for any y, I can find a unique x that satisfies this property. So I can define a function g for all elements of big Y using this specification. Okay, and then you can go from there. Show that this function g is an inverse of f. So show g is an inverse of f. Okay? All right. Now here's some other properties of bijection. Prove that any inverse of a bijection is a bijection, and then show that the inverse of a function is unique. There can't be two different inverses of a function. Yeah, that's an important point because because we do later on talk about a inverse of a function, and later on we'll see that in some instances functions form a group, and we need to have an inverse of a function in order to get a group of functions. Okay. All right. Now I kind of let the cat out of the bag, saying that functions, in some cases, form a group. Now, if we have a group, we're going to not only have inverse, but we need to have identity. So we're going to define an identity map. Now, if map is another way of saying function, this is a function. Typically, you talk about a map when you have a function from a set to itself. Then you call that a map. Okay, so here we have a function from a set to itself. The domain is equal to the range, and it's a function that takes every element just to itself. So you could kind of show it like this. If I have some element a here, a is going to go back to itself like that. Okay, the two things you need to show here: show that the identity is invertible and find the inverse of the identity. All right, I think you can just sort of think about that. What's the inverse of the identity? Okay. And here another proof about inverses, that they satisfy this composition law. Okay, a couple other exercises, and that's it for inverses.